ChatGerry, From Complex Stroke Mechanisms to the Simplicity of Arithmetic, number 1572, March 13, 2026, Gerald C. EclaireMD Foundation. Category: Mathematical Simplicity and Medical Sophistication. Introduction. On June 21, 2025, I suffered a hemorrhagic stroke. After surviving that event, my primary goal became very simple: prevent a second stroke. Instead of relying only on general medical advice, I decided to monitor my own physiological signals continuously and analyze them with mathematics. I built a personal medical AI system called Chronic on my iPhone. This system analyzes my daily health data and gives immediate feedback about my stroke risk. Every time I enter three key biomarkers, a glucose EG, systolic blood pressure SBP, and diastolic blood pressure DBP, and the system immediately calculates additional indicators. These include pulse pressure PP, mean arterial pressure MAP, SBP spikes, and several stroke risk indicators called the Stroke Triggering Sensitivity Index (TSI). Two of these indicators are especially important. TSI2 uses only blood pressure mechanics. TSI3B uses blood pressure mechanics together with CG and glucose data points. If my TSI values stay below about 100, I consider my vascular system to be operating in a relatively safe range for that day. If the value rises above 100, I am entering into a dangerous zone and immediately take corrective actions. These actions include reducing carbohydrates and sugar, walking after meals, practicing breathing exercises, inhaling for 4 seconds and exhaling for 8 seconds, repeated 4 to 5 times, and avoiding emotional stress. Each day I measure my glucose about 96 times and blood pressure about 20 times. These hundreds of daily measurements allow me to continuously observe how my vascular system behaves in real time. My hope is that this dynamic feedback system can help me prevent another stroke. To stroke sensitivity models, the first model, TSI2, focuses only on vascular mechanics. TSI2 equals SBP dBP over 45 times SBP 120 times 10 pulse pressure. SBP dBP reflects arterial stiffness. As arteries stiffen from aging, obesity, or long-term metabolic damage, pulse pressure increases. During the period from 1990 to 2009, my type 2 diabetes was poorly controlled and treated mainly with medication without major lifestyle changes, according to my viscoplastic energy analysis. This 2 decades period contributed about 91% of the total vascular damage that eventually led to my stroke. In contrast, during the following 16 years 2010 to 2025, when I controlled diabetes through lifestyle management without taking any medications, the additional damage was only about 9%. To capture this metabolic factor, I created the second model. TSI3 equals SBP dBP 45 times SBP 120 times EEG 140-120. Here EG represents estimated average glucose measured by a continuous glucose monitor CGM. Now Stroke Triggering Sensitivity Index (TSI) becomes the interaction of 3 factors: arterial stiffness, pressure, load, glucose damage. After my stroke, my blood pressure improved significantly, TSI minus the curve declined. However, my glucose increased by about 10% because the stroke disturbed my metabolic system, and post-stroke exhaustion reduced my daily physical activity. Since TSI3B multiplies blood pressure and glucose together, TSI3B curve did decrease, but it did not decline as much as the TSI2 curve. This difference reminds me that glucose control remains critical. Why multiplication matters? The reason the TSI model uses multiplication rather than addition comes from a basic principle in physics. 400 years ago, Isaac Newton described motion using the equation F equals m times the force equals mass multiplied by acceleration. Newton did not write F equals m plus a because that would not represent physical reality. Force emerges from the interaction between mass and acceleration. If one increases, force increases. If both increase together, force increases even more. Multiplication therefore captures interaction while addition assumes independence. This difference becomes clear in simple arithmetic of 2 interacting factors. 2 plus 3 equals 5, 2 times 3 equals 66 greater than 5. With 3 interacting factors, 2 times 3 times 4 equals 20, 4 to 3 4 equals 9. The multiplicative effect grows much faster. The vascular system behaves in a similar way. Stroke risk does not come from a single factor. It comes from the interaction between vascular stiffness, blood pressure, load, and metabolic damage. Mechanistic modeling versus statistical scores. Most medical risk models are statistical scoring systems. They usually look like this: risk score equals A1 times F1 plus A2 F2 plus A3 F3. Each factor contributes independently, and the contributions are added together. These models are useful for studying large populations. However, they do not explain the physical mechanism of failure inside a specific patient. Engineering models are different. They often describe failure as the interaction between multiple factors, such as structural weakness, applied load, and environmental damage. This type of model is naturally multiplicative. The TSI model follows the same principle. TSI approximately equals PP times SPP times EAGIT is not a statistical association model. It is a mechanistic interaction model. Viscoplastic energy and stress accumulation. Another concept used in my research is the VMT energy modeling of viscoplastic medicine theory, and this framework, system behavior, is described using stress and strain. One key quantity is strain rate, which measures how quickly strain changes over time. Stress is related to strain rate and other influencing factors. When stress and strain interact over time, energy accumulates in the system. In engineering, the energy generated during loading can be calculated as the area under a stress-strain curve. Calculus is used to calculate this area by adding many very small pieces together. In biomedical systems, similar ideas can help describe how physiological stress accumulates gradually and eventually leads to structural damage. Conclusion: the TSI model was developed for a practical reason, preventing another stroke. By combining continuous physiological monitoring with simple mathematical models, I created an indicator that reflects the interaction between vascular mechanics and metabolic stress. The comparison between TSI2 and TSI3b illustrates a key principle. Blood pressure alone does not determine stroke risk. Glucose and other metabolic factors can amplify vascular vulnerability. Real biological systems are rarely linear. Interactions dominate. The multiplicative structure of the TSI model makes it highly sensitive to spikes. For example, a 10% increase in glucose combined with a 10% increase in systolic pressure produces about a 21% increase in TSI. This sensitivity provides an early warning signal. Instead of being a passive observer of disease, a patient can become an active systems engineer of his own body. Final reflection: this work can also be viewed as part of a long scientific lineage. More than 400 years ago, Isaac Newton showed that complex physical systems could often be explained through very simple mathematical relationships. Centuries later, Professor Norman Jones at MIT extended Newton's thinking into sophisticated viscoplastic energy modeling to analyze structural behavior under dynamic loading. After more than half a century, I applied the same philosophy to human physiology. By identifying a few key interacting variables and expressing them through simple arithmetic relationships, the TSI model translates complex stroke mechanisms into a practical daily monitoring tool. In this sense, the conceptual trajectory runs from Newton's simplicity of physical law through Jones's sophisticated engineering analysis, and back again to the simplicity of arithmetic applied to biomedical physiology. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.